All right, if you look at the chart above here, I have an arrow pointing from elements to compounds, and then I have an arrow pointing from atoms to molecules. And below them, I have elements to atoms and then compounds to molecules. Now, what I mean by these arrows is that the elements are actually the one combining together to form the compound. And we said previously that the atoms are the smallest parts of these elements, and if these elements are combining, they are combining in these small parts until they are completely used up. Now, as they are combining in these small parts, they don't form the giant parts of the compound. They start by forming the smaller parts of this compound, and the smallest part of the compound is what we call molecule. So the compound is what is formed when elements combine together, and then the smallest part of the compound formed is the molecule, and the elements that are combining together combine in small fractions, and the smallest part of the atoms that are combining, the elements that are combining, are called atoms. So what we're trying to say is the atom is the smallest part of the element, while the molecule is the smallest part of the compound. So now let's take an example, an element sodium combining with another element, chlorine. When sodium combines with chlorine, they form sodium chloride. Now, sodium is an element, chlorine is an element, and the sodium chloride formed is a compound, because we say a compound is a substance that is formed when elements combine together. I'm going to give us the detailed definition of these concepts after I'm done explaining this chart. Now, sodium combines chlorine, sodium elements, chlorine elements combine together to form a bigger substance called sodium chloride, and that bigger substance is what we call a compound. And we say the smallest parts of these elements that are combining are called atom. We say an atom is the smallest part of an element which can take part in the chemical reaction, and it is taking part in the chemical reaction. So the atom is the smallest part of sodium and chlorine that is combining to form sodium chloride. And the sodium chloride also has a small part, and the small part of sodium chloride is what we call the molecule of sodium chloride. So if the smallest part of an element is called an atom, the smallest part of a compound is called a molecule. Just assume water. A droplet of water has the same properties as a bucket of water. There is no difference. The only difference is in quantity. Are you getting it? Now, the quantity of a molecule is smaller to the bigger compounds on its own. So a molecule is the smallest part of the compound, while an atom is the smallest part of the element. The atom is the element and the molecule is the compound. It's just like I have these elements combining to form compound, and the atoms can combine to form the molecule. So I can write this like this. I can say a molecule is a substance that is formed when two or more atoms combine together. So a molecule is a substance that is formed from the combination of two or more atoms, because a compound is a substance that is formed from the combination of two or more elements. So when these elements combine together, they form the compound. And when the smallest part of the elements are combining, they form the smallest parts of this compound, which is called a molecule. Now, forgive us if you're a professional. We know we're actually starting very slow. We want to make sure that everybody is carried along, and it can get as complex as it can be. We urge you to kindly stay with us as we keep explaining this concept. We have actually explained the atom, molecule, the element, the compound. This is not a general explanation, as we're going to meet them as we grow on, but we just want to clear this part so that the students will be carried along as we are moving. So we're done with atoms, molecules, elements, compounds. We'll look at mixtures, valencies, ions, radicals as next. Now, as we've explained earlier, valency is defined as the combining power of elements. Now, if an element, let's say sodium, wants to combine with another element, let's say chlorine, now sodium is combining with chlorine in a certain way. Now, the understanding of the concept of valency is going to clear up to us how this combination are actually taking place. Now I'm going to give us some samples and then we're going to analyze them before going into valency completely. Now if we look at the samples of this chemical equation I've written on the board, you are going to find out that these are three sets of elements that are combining with chlorine. On the first one we have sodium, we have calcium, and we have aluminium. Both of them, the three of them are combining with chlorine. Now you can see that the product differ in some aspects. You look, sodium combining with chlorine will give sodium chloride, calcium combining with chlorine gives calcium chloride, and aluminium combining with chlorine gives aluminium chloride. And you can see the numbers of chlorine, the atomicity of chlorine here is changing. We know that the atomicity is defined as the total number of atoms in a molecule of a compound. Now if you look at this, you have 3 chloride atoms here, 2 chloride atoms here, and an atom of chlorine here. Why is it that when sodium decided to combine with chlorine, it is written NaCl, but when calcium came, the chlorine was having 2 atoms, and when aluminium came, the chlorine has 3 atoms. Now this has to do with the valency, because we said the valency is the combining power of these elements. As they are coming together, they come with a certain degree of power in which they exchange within themselves, and then they give this desired product we are seeing above. Now we have to understand what the powers are, then before we start bringing out the combination. Now, as we have explained earlier, we said that the number of protons of an atom gives the atomic number, meaning if an atom is number 2 in the periodic table, it is telling us that the atom has 2 protons. If an atom is number 20 in the periodic table, it's telling us that the atom has 20 protons. And based on what we have learned so far, we know that the number of protons is always equal to the number of electrons. So the number of protons balances the number of electrons. So an atom that is number 15 in the periodic table has 15 protons and at the same time has 15 electrons. Now it is this number of electrons that we are actually interested in, because they are the ones that keep on changing and they are responsible for the combination of different kinds of elements. So the electron is responsible for any kinds of chemical combination we see. Now we're going to look at how we write the electronic structures of these electrons based on the atomic number in the periodic table. Now, as we all know, the atom looks exactly something like this, and it has 3 subatomic particles, as we've explained before. We have the proton and the neutron, which are inside the atom, that is inside the nucleus of the atom. Then on the shells we have the electrons. Now the number of electrons keep increasing, reason being why the numbers of shells are increasing. And this is the first shell, the second shell, the third shell, and that is the nucleus inside. And these shells have a particular numbers of electrons that they allow to stay on them. Now the first shell, the inner shell, is called the K shell, then followed by the L, M, N, and so on and so forth. So now because we have these shells, we can just bring them out. Instead of having this bogus diagram like this, we said, okay, we call the first shell K, the second L, M, N, O, P, and so on and so forth. Is that clear? Now these shells, they have a particular number of electrons they allow to stay on them. Now for the purpose of what we want to do right now, we're going to assume that the K shell takes 2 electrons, 8, 8, 8, 8, 8 all through to the other shells. So we're going to bring up something that negates this as we approach, but now I want us to accept it like this. The K shell takes maximum of 2 electrons, the L shell takes 8, M8, N8, O8, and P8. So now we're going to take the atoms one after the other and understand how their valencies would be derived from their electronic structure. Now the electronic configuration of this atom simply means how the electrons of this atom are arranged. How the electrons are arranged. Since we know the K shell takes 2 electrons, we say on the K shell here we have 1, 2 electrons. Now since we know the L can take up to 8, we have 1, 2, 3, 4, 5, 6, 7, 8. So whenever we hear the phrase electronic configuration, it simply means how these electrons are arranged at the different levels of these shells. So now instead of arranging them on a circular atom like this, we want to arrange them in this way. Then this arrangement is going to lead us to understanding what valency actually is. Now, since we have understood that the K, L, M, N, O, P are representing the shells of the atom, so now we're going to start putting the electrons on them so that we understand. Now, hydrogen is number 1 in the periodic table. This is telling us that hydrogen has 1 proton, so automatically it has 1 electron, because we say the number of proton is always equal to the number of electrons. So if hydrogen is number 1, hydrogen is going to have 1 electron. So we have 1 electron on the K shell, because the K shell can accommodate up to 2. So helium, now helium is number 2, so helium is going to be 2, because the number of proton is 2, the number of electrons is also going to be 2. Then lithium, which is number 3, remember the K shell can take maximum of 2 electrons, so we're going to have 2 remainder 1 under the L shell. Then after lithium we have beryllium. It has 2 remainder 2, because beryllium is number 4 in the periodic table. So that's how it continues going. If I have, let's say fluorine, fluorine is number 9, I'm going to have 2, 7. So I keep going like this. If I have bigger elements like magnesium, magnesium is number 12. So magnesium is going to be 2, 8, 2. That is for magnesium. So it has 2 filling the K shell, it has 8 filling the L shell, then that is total of 10, we have 2 remaining in the M shell. So now that is how the electronic configuration are written. Element like calcium, calcium is number 20, going to be 2, 8, 8, 2. Remember, these are taking 8, 8 as their maximum, and the last 2 is under the N shell. Now there is something we are after. Now this last electron in the last shell is what we're after. If I have for lithium, for instance, lithium is number 3, 2, 1. This is the last electron. If I have for sodium, sodium for instance is number 11, 2, 8, 1. This is the last electron. So this last electron of every atom is called the valence electron. So the last electron is called the valence electron. So whenever you draw the electronic configuration of any atom, what you should be after is the valence electron. Let's take aluminium for example. Aluminium is number 13, so aluminium is going to be written 283. So the last electron of aluminium is called the valence electron. Now this valence electron, they differ between 1, 2, 3, 4, 5, 6, 7 and 8, because we have total of 8 groups in the periodic table. So the valence electron is either it is 1, either it is 2, 3, 4, 5, 6, 7, 8. Now if you look at this atom, whenever the shell completes 8, it moves to the next shell. Now the valence electron is a very important tool in identifying the valency of compounds. Some students might think that the valence electron represents the valency to some extent. Yes, but we are going to classify them in order to differentiate where does valence electron serves as the valency and where it doesn't. So remember, the valency is the combining power of elements. So the last electron after drawing the electronic configuration like this is called the valence electron, and it is this last electron that will give us the result on what the valency of an atom or an element is. So as we've explained earlier, the valence electrons are always between 1, 2, 3, 4, 5, 6, 7 or 8. So the valence, whenever we draw the electronic configuration of any element, the last electron, the valence electron, is either going to be 1, between 1 and 8. Now these valence electrons are not their valencies. To some extent they are, but we're going to classify these valence electrons and see which part where the valence electron becomes the valency, and in which part is the valence electron not the valency. So I have 3 classifications here. I've divided them into 3 groups. I have valence electron 1, 2, 3, 4. Valence electron 1, as in the case of sodium, sodium is number 11, so it is 281. The valence electron there is 1. Lithium is number 3, it is 21. The valence electron there is 1. So, and so many other elements. We have elements that have valence electron of 2, like magnesium, 282. The valence electron is 2. Like calcium, 2882. The valence electron is 2. In the case of 3, we have aluminium, 283, which is number 13 in the periodic table. It is having 3 as the last electron. So the valence electron is 3. We have carbon, which is number 6, having valence electron of 4, that is 2, 4. Alright, let me use the following question to perfect the knowledge of our valency. Now we're going to draw the shells, which are K, L, M, N, and so on and so forth, and we're going to start drawing the valencies of different elements. Now we're going to make this very, very brief. Now, what is the valency of oxygen? I know oxygen is number 8 in the periodic table, so I'm going to say 2 for K shell and then 6. So I have 2, 6, and since 6 now is the valence electron, it is more than 4. I'm going to check how many is left for it to be 8. 2 is left for it to be 8, so the valency of oxygen is 2. Now, what is the valency of sodium? Now, sodium is number 11 in the periodic table. It's going to be 2, 8. This is filled up, and we'll have left with 1. And the valency of sodium is 1 because the valence electron is between 1 and 4. Remember, we say when the valence electron is between 1, 2, 3, 4 is equal to the valency. When it is more than 4, that is when we check how many is left for it to be 8. Like in the case of nitrogen, what is the valency of nitrogen? Nitrogen is number 7 in the periodic table. We have 2, 5. We have 2, 5. We don't say the valency is 5. This is the valence electron, but not the valency. Now it is more than 4. If it is more than 4, we check how many is left for it to be 8. What is left here is 3. So the valency of nitrogen is 3, not 5. If I say, for instance, what is the valency of fluorine? Fluorine is number 9. So I'm going to have 2, 7, which is 9, and then the valence electron is 7, and it is more than 4. I'm going to look at what is left for fluorine to be 8 is just 1. So the valency of fluorine is the same as the valency of sodium. So the valencies must range between 1, 2, 3, 4. For instance, carbon. Carbon is number 6, and then the structure is going to look like 2, 4. Carbon has 4 as the valence electron, and the valency is equal to 4. So what have we learned? If the valence electron, that is the last electron, is between 1, 2, 3, or 4, is equal to the valency. Now, if the valence electrons are greater than 4, that is, it ranges between 5, 6, 7, we're going to check how much is left to get the valency. Now, for 5, I have 3 is left for it to be 8. Then for 6, I have 2 left, and for 7, I have 1 left. So if I have element like chlorine, which is fluorine, which is number 9, it is 2, 7, and 1 is left. So that 1 that is left to make it 8 is the valency. What about those elements that have 8 in the outermost shell? Now these elements are very, very stable. The reason why we need the valency is to combine. What is the meaning of valency? Valency is the combining power of elements. And why do elements combine? They combine to be stable. These guys that are having 8 are already stable, so there is no need for combination. If there is no need for combination, then there is no need for valency. Example, we have helium. Helium is complete, it doesn't combine, so it needs no valency. Argon, neon, krypton, xenon, radon are examples of these elements that have octet configuration, and they are very, very stable, so they don't combine. So I hope this will help us to understand how to get the valencies of various elements, that is their combining power. And when we start writing the chemical equation of substances, you are going to know the big advantages of this valency.